Okay, this is lecture number 28, and somehow something happened between while I was making this lecture number, and the first part was not recorded. So I'm redoing the first part, and from the second part there might be a slight jump, but I guess you will be able to sort of understand it. I just don't want to do the whole thing all over again. So the important part that we had discussed before, and I would like to re-emphasize, is that the typical, we will be talking about fluvial sediments to start with. We will be talking about fluvial sediments. So it starts from a high ground, essentially, and then there is a slope here, and this is from the hills to the plains. And then the river flows down, and finally there is a water body into which the river system unfolds. What happens is, as you know from the Hillstorm diagram, that in this part it's mostly weathering and erosion. It's mostly weathering and erosion. Here it is mostly erosion and transportation. And finally, this is the place where you deposit your sediments. So you can imagine the river Ganges. It starts in the Himalayas somewhere, way up, and then all along UP, Haryana, UP, and then Bihar, Bengal, and then it goes into the Bay of Bengal. So this whole sediment could drain into a landlocked water body, and you could also have another river flowing down from some other angle. You could have multiple rivers draining into the lake. It's not very common, but you may have such situations. Or else, you can have a situation where, say, this for example is the mean sea level, and this is the oceanic part. This, if you remember, is the continental slope. This is the abyss, and this is the continental margin, and this is the continental shelf. So you can have a sediment that is being deposited as materials are being transferred from the hill down the plains and finally into ocean basins. Now what happens here is the materials that flow down here into an ocean basin and into an abyss. And here sometimes, because you can see here the sediments are coming down at very high speeds because of the very sharp gradient, and then opens up into the sea, so you can have sediments being deposited also here. These are submarine, and this is on continental areas. So sediment deposition can also occur, as you see, on the banks of the river. It can be at the foothills of the Himalayas. It can be in the marine environment. It can deposit anywhere. And you can have landlocked areas where multiple rivers can drain in. So there can be very varied situation in which things can happen. Now, an important aspect of this deposition is you must understand two things. Here, for example, if I take this part, here, for example, the total length of the water body is quite high. Length of the water body is very high. But these water, the sediment laden water, when it comes, the effective density of that water is much higher than normal water without sediments. So what happens, although this river flow into the sea, they do not flow right away, but they hold on to the base of it and then they deposit the materials here. So although there is a large column of water here, the effective length over which the sediment separates is small. Although the water column is large, but the effective length over which sediment separates is quite small. That's an interesting situation. If you separate it from this part, where from the hills onto the slopes materials are being deposited, here the deposition occurs over a small thickness, but the water, available water, is also very small. It's also very small. Have you understood? So here the total length of the water column is as small as the length over which things happen, and this is over the length over which it deposits. So when you look at sediments, they have a complicated history. Now we come to a term which is called the settling velocity. We come to a term which is called the settling velocity, where mu is given, this is given by what is called Stokes' law, where W is equal to 2 into rho solid minus rho fluid into G into R square by 9 mu. This is what is called the Stokes law. Now the Stokes law is not valid all over the place. It has certain restrictions, and just a moment, please. There is something called Reynolds number. Reynolds number. It's given by the term RE, Reynolds number, RE. And RE is given by the equation H into U into rho and the whole thing divided by mu, where this is the kinematic viscosity, H is the channel width, is the channel depth, U is the velocity, and rho is the density, as always. Now, for Reynolds number, which is a dimensionless quantity, Reynolds number greater than 2000, and this was cause turbulent flows. Could cause turbulent flow. And Reynolds number less than 2000, this will cause laminar flow. Turbulent flow and laminar flow. Now, what is turbulent flow? We don't go into the details of the turbulent flow, but I think it is important, where essentially in laminar flow the situation is something like this. say if you take this the river and this the river bed, and this is, as I said, was h, and this is the velocity profile of a river. This is the velocity profile of a river, and this velocity maximum occurs at 2/3 the 2/3 h velocity maximum. In this, the velocity increases systematically in this direction and then decreases because of the resistance of the wind. It's not as sharp, it's much higher, but this is what happens. So essentially, here the velocity is close to zero at the base, then the velocity increases, and the velocity increases, and the velocity increases, and again decreases the velocity. So this is how the velocity of a river changes. Right? Now, in a turbulent flow, the similar thing happens, but only thing, there are more turbulences and eddies. So say once again, if you have the riverbed and if you have the surface, then again the velocity profile is like that. But here, your waves are like this. The waves are like this. That's the turbulence that it creates. So it's not a very laminar flow, it's a very turbulent flow where eddies are generated, and so velocity variations are not as smooth as the laminar flow. The discrimination is at 2000, Reynolds number 2000 where it's a laminar flow, and Reynolds number less than 2000 is laminar flow, and Reynolds number more than 2000 is a turbulent flow. No. So now, so you see, the Stokes law is calculated for Reynolds number equal to or less than 0.1. That is what the Reynolds number, the Stokes law refers to it. At Reynolds number 0.1. If you compare to a Reynolds number 2000, this is purely of laminar flow and the velocity is very, very small. So it's almost like a stagnant water where settling is occurring, the Stokes law is occurring. So essentially you have a complete, almost stagnant water where a material, a particle grows solid and you have material flow around it. So this is the particle gravity drawing downwards, and this is the drag caused because of the fluid through which it is passing. So when this force is more than this force, obviously the particle would settle, start moving downwards. But if this balances, then of course the particle is kept in suspension. It doesn't fall off. But since the Stokes law is very interesting in many ways, because as you can see, this W is equal to a function of rho s and r squared. That's an important point, because we are taking all fluvial sediments, so the density is 1 gram per centimeter cube, and this mu is almost a constant. So what happens is, your settling velocity, therefore, is a function of rho s by r squared. That means the settling velocity will increase the larger the diameter of the sphere, or the radius of the sphere, or the density of the particle. So if the density of the particle is high, W will be high. If it's large in size, the W of the particle, the settling velocity of the particle would be high. So you can take as a simple case here, but this so this is the important fact. We will talk a little bit about it just in a wee bit moment. But for higher Reynolds number, this is a very low Reynolds number. For RE value around 1000, Newton modified the settling velocity. W is equal to 2.4 0.46, and this is rho s minus rho f by rho f into g into r divided by rho f by gr and this half. So this was given by Newton for the settling velocity. But the important point is, most things are the same only here, and here you have rho s and r as the functions of the settling velocity. Rho s and r are the function, although the functions are slightly different here for higher Reynolds number. But once again, you can see your settling velocity is directly a function of the rho of the particle and r, which is the density of it. So, if we then do the following, so say for example, if you have a long jar like that, and if you put in some sand here or some particles of having different sizes, these particles will have different sizes if you put it over a long, very long jar, then the important point that happens is, as the settling velocity of the larger particles are more and the settling velocity of the finer particles are less, and if they are of the same density, then the larger particles will deposit at the bottom, and the younger particles, they will deposit at the top. So you have the larger particles here, and this you have the younger particles here. This is a consequence of a natural phenomenon of settling velocity. So what happens is, in a through section, which is correct, you have the larger particles at the bottom and the younger particles at the top, and this is called graded bedding. Where you have different layers having different sizes, with the younger sizes towards the top. If you then have a situation where it is reverse, say for example like this, larger particles, and then you have smaller particles this way. If you have this section, then you see these are the larger particles upstairs and these are younger particles upstairs. Now you can say that it would be impossible to do it. Natural process, this cannot happen. In other words, this geologic section is inverted. How inversion takes place, that we will talk later on. But this is an inverted section. This is not a normal section. This section is a normal section where the younger sediments are to the top and the older sediments are to the bottom. So this is one thing, is about the settling velocity. Now, if in the other hand you can imagine, if you take sediments with the same radius but of different densities, if you take sediments of the same radius but of different densities, then those minerals having the higher density will settle faster, and those with the smaller densities will settle later. So what will happen? The sediment will now become layered because as per the density of the particles. So there will be a mineral segregation as a part of the bedding plane. So one layer of one mineral, the other layer of other mineral, the other layer of other mineral, but the density should decrease from bottom to the top if all the sizes are the same. Now you can have a combination of all this, and you can see it can become very complex. So the important point here is, but one thing is sure, I am talking about here a deposition, and this will be most efficient where the water column is very long. If the water column is very long, it will be very efficient. But if the water column is short and you do not allow the materials to move down under the influence of gravity slowly over a considerable length, these variations according to size and density will not. So what will happen for sediments which have been deposited over short distances and sediments which have been deposited over long distances, they will be very different. They will be completely different. So here, for example, if the distance length traveled is very small, there may not be effective separations of the densities. It may not be. But if it is very long, if the sediments were deposited here, then it would have been deposited. The other point that I should mention here, that I think that's about all, and then I think the next video should be a continuation. There might be a little discontinuity. Please try to manage. And once I upload this set of 4 lectures that I have now of sedimentary rocks, I will send you also in my post a particular, a particular site where it is given as I promised to you when I discussed with you. But there are many other sites you can look for it. Thank you. Thank you very much. Okay, we start with the discussion again. So if I take materials of the same density, and we put it on a jar, on the top of a long jar, for example, and we put on it, then the ones with the larger radius will have a faster settling velocity, and it will settle to the bottom. And progressively, smaller and smaller particles will deposit the top. So the younger sediments will be smaller in size. This term is called graded bedding. Graded bedding. It's a very famous feature of sedimentary rocks. Now, this is very important that this is young and this is old. This is typically used for finding young and old sequences. Whether, say for example, if you have this one, then you know that your top means young. But say for example, if you have this situation, then you see this is old and this is young. That means to say it cannot happen. It can never happen this way. Natural processes, it will never happen this way. If it does not happen, then this section, the old at the top, is somehow inverted. How inverted, we will come to that later. But it is not a normal section. It's not a normal section. This section, if it is there, it's not a normal section. This is a normal section because of this same logic. So what happens is that you get a graded bedding. If you take the Stokes law into consideration, and you can understand if you have, say for example, two types of materials, two types of minerals, say mineral A and mineral B, which has rho A and rho B is the density, and they have the same radius. The radius is the same. Then what you will have? You will also have the one with the higher density, because they have the same radius now. They have the same radius now. If they have different densities, then the one with the heavier density will deposit first, form a layer, and the ones with the lower density will appear at the top. So you will have a bedding, you will have a gradation, but this gradation has got nothing to do with the size. It has everything to do with the density of the material. And obviously, I have not said it would be with the density of the material. So what happens in sedimentary rocks sometimes, what you see is, you see a wonderful bedding plane by which you deposit the materials in layers after layers and layers, and suddenly you will see a layer consisting of some minerals, finely thin layer. That might be a layer which has a different density than the other layers making it up. But as I said that this settling velocity, so we get this point that you have what is called the settling velocity, and in Stokes law for values of Reynolds number 0.1 and lower, that means almost no velocity, complete laminar flow, the settling velocity is given by this equation, where it is dependent on the density and the square of the radius, but is inversely proportional to the kinematic density. So if you have higher mu values, that means more viscous material, then of course there will be more drag, and this will reduce the settling velocities. So it's all very understandable. But the Stokes law has a limitation because of the Reynolds number. It has a limitation because of the Reynolds number. So what happened, there was another great gentleman at that time who seems to be there everywhere, said, he suggested the following equation. W is equal to 2.46 rho solid minus rho F into G into R divided by rho solid, rho fluid. And this to the power half. This works for Reynolds number 0.2 to 1000 Reynolds number. And this great gentleman, for giving this settling velocity, is no other than Isaac Newton. So this is called the neutron's drag. There is also called neutron's drag. This is the basic equation. This is the basic equation, which is slightly different from that of Stokes law. But the basic fact, dependence on R and dependence on rho s by rho f. You see, this is rho s by rho f and this is minus 1. So basically, the main differences are still the density of the solid and the radius. Although the velocities would change by magnitude, but the functions remain almost similar. So what happens is that this works much better for Reynolds number 0.2 to 1000, still laminar flow. Still laminar flow, because laminar flow is overcome by turbulent flow when at 2000, when Reynolds number is greater than 2000. So this is what it is all about. And this is what is graded bedding, and this is what is normal bedding, young to the top, and old to the top is a sequence that is inverted. Why inverted? We will talk about it later. So this is what happens. So now what happens, because now you see here, I have told you that I have told you that if you take a very long jar with water in it and you pour in some materials, they will fall through this and segregate into different sizes with the younger occurring at the top. Imagine a situation where this long jar means that the water level is very high. The water level, the length of the water column is very high. Now, imagine a situation where the length of the water column is not high. The water column is high, but the total distance over which this mineral segregate according to size or density, that column is small. Look at here. Look at here. This has a long water column, maybe several kilometers, maybe more than 1 kilometer. But if the sediment-laden high-density water is restricted to the bottom, then you see the total effective length over which segregation occurs remains small. Have you understood? So it is, have you understood? Here, although the length of water column is very long, but the total effective length over which this differentiation according to size is very small compared to that. So what happens? Although there will be some differentiation according to size and density, but it will not efficiently segregate material from coarse and systematically fine. This won't happen. What you will have is an aggregate of particles, which are not particularly well separated. Not exactly separated according to size. There will be a mix-up. So normally what happens, when you get a sediment, you don't get only one size. You get different sizes. Not only one size, but different sizes. So it is important that we try and look at the size classifications of the sediment once more. How do we do it? Normally what happens, so once again, just before I erase it, so sediments here also, say for example, when the sediments are settling, what is the difference between this part and this part? The difference is, here the total water column is very long, but the deposition is occurring over a very short distance. So segregation or differentiation according to size and density is not being effective. Here what is happening? The water column is small. The water column is small. So effective segregation will not happen. So there are two things. One is the actual water column, and the other one is the effective water column over which the differentiation is occurring. It will do the same damage to you. It will do the same damage. So you will have normally, and then for example, if you have such a situation where in a particular depression, could be a lake or something, materials are being deposited from multiple river systems, then all the river systems are not bringing you the same material. They are bringing you different material. And remember another thing. What happens is, if you take a sediment column, a column of sediments, you know during the monsoon there is a lot of water in the river. So what it does is, and the speed of the rivers are also much more. The total channel, the total bulk of water and the speed of water is much more. Right? So, but as the monsoon session ends and we go through to the winter and summer, the total amount of water that is coming into the rivers is much smaller, and they are coming at slower speeds. So what happens over a particular year, for example, in a yearly scale, the dynamics of the river system is also changing. During the monsoon, you have a high speed. So you know from the Hewlett-Stone diagram, etc., that the metal sedimentary load that it is carrying will be slightly different, from those during the autumn, during the winter season, and during the summer. It will be very small. So what will happen is there are changes in the grain size patterns which can vary over a year, from summer to monsoon, and summer to monsoon. This cycle will completely changes. So what happens when you take a sediment? It is almost always, you don't get one size of sediment. You get multiple sizes of sediments. And therefore, there is a need to statistically separate it. This can be done, the statistical separation and analysis of grain can be done on loose sediments, unconsolidated sediments. For consolidated sediments, what is happening? First of all, I told you from unconsolidated to consolidated, it goes through lithification. Lithification involves compaction. Lithification involves pressure solutions. Lithification involves replacement of minerals. So what happens? The grain shapes change. To start with, the actual grain shapes are changed because of these effects. And second, in a lithified rock, which has become now very strong, it's very difficult to separate individual grains because they are now locked in. As is different from you go to the river now and you pick up unconsolidated sediments and you will have them all loose. So it is better to analyze loose particles. But if you take a consolidated sediment, you can't look at it in a third dimension. They're too consolidated. You still can work with them, but that would require only two-dimensional analysis. Otherwise, for a loose sediment, you can do it a three-dimensional analysis. So normally you can do it, and I will try and lay down the foundations of such a work. And it is also, before I go into that, I should also remind you a few important things. Say, for example, if the transport distance, say from the Himalayas to the Bay of Bengal, the river Ganges flows to several thousands of kilometers. So the transport distance is very long. But there are many rivers that do not travel so long. Some rivers, say for example in mountainous terrains, what happens? There are valleys along which the rivers are, and from the top, rivulets join the main river as rivulets. So what happens? There, the transporting distance of that rivulets straight down is very short. So what happens? If it is very short and the transport distance is short or the transport distance is long, what is the difference? If you have a long transport distance, then you will expect that you will have tremendous amount of grain size reduction, high increase of sphericity, increase of roundness. But if you have short distance of travel, then what type of grains will you get? The grains will be coarser, the grains will be angular, the grains will be non-spherical, because no grain is formed spherical. Okay, so what happens for short distance transport? You expect grains to be angular or subangular. You expect the grain to be low sphericity, low roundness. Similarly, grains, materials which are traveled far, you would expect tremendous grain size reduction, tremendous increase in sphericity, and tremendous increase in roundness. You will see it. Especially this roundness and sphericity is most pronounced when bed load movement is very high. Once the bed load percentage decreases sharply, then what will happen? Materials are easily, when you're just transporting a suspensions, there is no abrasion. There is very little reduction in grain size, of course. Now there is one more thing I will say before I conclude this section. The important point here is, when I say the distance of transport, I told you from the Himalayas to Bay of Bengal, thousands of kilometers. Yes, I'm right. But if you go to the beach, what do you see? You see the sands being brought in, the sands being taken back into the sea, the sands being brought back again onto the beach, again taking it to the sea. So maybe the total distance over which it is traveling in one cycle is very small. But when you take it over time, integrate over time, then the total amount of to and fro distance that it travels should be very high. Because, okay, the distance of movement, of single cycle movement is not very high. But multiple cycle, it's moving over several hundreds of kilometers. So the transport distance does not move a linear one type of movement. it can also involve to and fro movements. This will also cause a lot of abrasion. In fact, the sediments, the beach sands, are some of the best sorted sands in the world. Some of the sands are some of the best sorted sands in the world. So that is what I'm saying. So when there is long transport distance, one cycle, or it could be multiple cycle short transport, and yet you will get the total result would be very much the same. So having told you all this, I think you can understand now. When you see a particular sediment deposited somewhere, maybe in a riverbank, maybe in an ocean basin, maybe somewhere from the hills to the slope, wherever you see, you're unlikely to see sediments that have only one size. They don't have it. Normally, they don't have it. So they have multiple sizes. And they have multiple characteristics. They could be angular if the distance between the site of transport, site of weathering to the deposition site is small, they will be angular. If the distance is long, then it will not be angular, that will be rounded. Or to and fro and aft motion, but over a long time, it will also give you it will also change the grain characteristics. So what I am talking now of, grain morphology. How does the grain look like? But there is also something which I will not tell you. If you take the grain under look at microscope, they give you tremendous characteristic features. And from that you can say what type of rocks, because they represent a part of the broken rock, what type of rock was sampled. But that is when you look at the internal structure of the grain. Since I have not taught about it, and all this requires a lot more understanding, which I have not told you, and maybe you're not aware. So what happened? I am not talking about how provenance or source rock characteristics is determined. I'm more or less talking about grain size, sphericity, roundness, morphology of the grain, and trying to build up how from that you can find out the depositional and transportational characteristics of a particular sediment. So now let us focus on the what should I say, on the grain size. Now, what happens if the grains are diverse sizes? I'm talking of unconsolidated sediments, as I told you before. Unconsolidated sediment. If I take an unconsolidated sediment, I expect it to have different sizes. And you know the sizes can be put as conglomerate, pebbles, boulders, pebbles, cobbles, sand, silt, clay, etc., etc. And you know the total range I have already given you, wooden Whitworth scale, so you can do it. So what you do is you take a you take a sort of a machine which has a flat bottom. There's a cup at the bottom. And there are cups like this. There are, what are these called? And then you have a lid. Yeah? What are these called? These individual ones? Sieves. No, okay. And this is what you take, you know, you have this, some old days you had this tiffin carrier thing, that you have a box and you have a box and you have a box and a box, and you put one over the other, rice, sabji, dal, etc. And then you have put in. What happens is, here, this is a section of it. This is put on a machine which can vibrate on different axes. So, what happens is, you can put something at the top. And lock it and start to vibrate. So what will happen? Materials will drop down. Now if I look from this side, the sieves have a circular shape. I'm saying from here or down into each of the sieves. These are made of brass. And they have fine strings. You know, very, very fine strings are tucked. A very fine string. I don't have the patience to draw it. So it's like a net, or it's called a sieve. It's called a sieve. So what happens? This area, say any area in this sieve, is the same. So what happens? It will only allow a particular material of this area to go through it. Those which are smaller will go through. Those which are larger will stay on the sieve, and those which are smaller, this will go down. So what happens when you take this sediment and put it on the top, and here you have a vibrator, and allow it to vibrate in different axes. So what happens? The sediments start trickling down. Have you understood? The sediments start trickling down. As it trickles down, say the total weight is W0. The total weight of the sediment is W0. Have you understood? And say this one, the sediment is 0, this is W1, this is W2, this is W3, and this is W4, and this is W5, W6. So W0 is equal to now W1 plus W2 plus W3, etc., etc., etc. Now, if I take, say, W6 divided by W0, this fraction, into 100, what is it giving me? It is giving me the percentage of this weight, that means between this size and this size, between this and this. Say this is 2 millimeters and this is 1 millimeter. So between all this material here have the size between 2 millimeter and 1 millimeter, and they form, say, W5. So all those materials which are between 2 and 1 millimeter, and they have a weight W5, and I divide it by W0 into 100, I will get a fraction, a percentage value. That means all the grains between 2 and 1 millimeter occurs in that percentage. Have you understood? So if you add these percentages up, it will add up to 100%. It will add up to 100%. So what we will do after that, so we will write 8 millimeters, 6 millimeters, 4 millimeters, I'll just give you an example, 2 millimeters, etc. So 8 millimeters to 6 millimeters at 20%, 6 millimeter to 4 millimeters 40%, 4 millimeters to 6 millimeters is again 15%, and less than this is 60, 75, 25%. So what I do is, this is called the class interval between 8 and 6 millimeters, and they consist 20%. So between 6 and 4 millimeters, they are 40%. Between 4 millimeters and 2 millimeters, they are 15%. So what I get is a probability, a statistical measure of the total, the number of sizes, and what is the fraction of the size in the total sample. I get it. That's the word I get it. Now I can tell you that in consolidated rocks, this is not possible, because it's not loose. And the shapes have changed because of dissolution, replacement, all these things. The shapes have completely changed. So you can't do it for a consolidated rock. But for an unconsolidated rock, you can do this. Okay, I think I will continue in the next class. Thank you.